Hello, we are going to solve some questions from CBSE textbook today. Here is the first question from the CBSE textbook. Now let's take a moment to read this question. Now this is one of the things which you would want to do very well when you take any test or exam, that is read the question. So take some time to read the question thoroughly, and if you look at this question is also structured in a way that there are multiple parts to it. So take some time to understand the structure of the question. Now I'll read along with you for this. It says, Coulomb's law for electrostatic force between 2-point charges and Newton's law for gravitational force between two stationary point masses both have inverse square dependence on the distance between the charges and the masses respectively. This is what we are expected to do. Number 1, compare the strength of these forces by determining the ratio of their magnitudes. We have to do that 2 times, one for an electron and a proton, then for the second time for 2 protons. This is the first part of the question, which itself has 2 parts. Next, estimate the accelerations of electron and the proton to the electrical force of their mutual attraction when they are 10 to the power minus 10 meter apart, which is also called as 1 angstrom. For this they have also given us some constants: mass of proton, mass of electron. Now let's come back to solving this question. This question is fairly straightforward and simple. Here we are speaking about 2 forces which are acting between an electron and a proton. Okay, so this is an electron, this is a proton as a positive charge. Now we are looking at the various forces which are acting, particularly 2 forces. One is because of the positive and the negative charge, they experience some forces due to the electrical charge, that is Fe. In addition, there is also another force which is due to the attraction of one another, which is called the gravitational force. Now we have to find both these forces. Now as for the first force, which is the electric force, we already know, we have derived the formula for that, 1 by 4 pi epsilon naught into q1 q2 by r square. We know the formula for this already. Now if you look at the gravitational force, it in the formula it looks very similar to this, which is force due to gravity, small g, capital G, whatever, is given by G into m1 m2 by r square. We have these 2 different formulas. Now this question is asking for a ratio of these forces. Let me keep it as small g. So we are looking at Fe by Fg. Can we do that? Yes. Simply go ahead and substitute this: 1 by 4 pi epsilon naught q1 q2 by r square into r square g into m1 m2. Now we could proceed with cancellation of the terms in this. This gets cancelled. Now this part I could directly take it as the Coulomb's constant, which is 9 into 10 to the power 9. So let's take that as a constant. Then we are speaking about q1 and q2. Now what is q1 and q2? They are the charges of the electron and the proton, which is same, 1.6 into 10 to the power minus 19 square. Then we have this universal gravitational constant, which is given by 6.67 into 10 to the power minus 11. Now as for this part, which is m1 and m2, we go with mass of proton and mass of electron. So we have already seen that mass of proton is given by 1.67 into 10 to the power minus 27, and the mass of electron is given by 9.11 into 10 to the power minus 31. So you can easily make an observation here that a proton is several times heavier than an electron. So mass of a proton is much higher than the mass of an electron. So when we substitute all this value in the equation, I'm not going to focus on the actual computation of these values because we already have substituted the required numbers. You get 2.4 into 10 to the power 39. That is the ratio that shows Fe is much greater than Fg. So we have solved the first part of our question. Now what happens if instead of having 2 electrons we have 2 protons? Both of them are brown colored bodies, protons. Now they are not going to repel, they are not going to be attracted, they are going to repel each other because they are both positively charged. Now what changes in this? Nothing much changes except for only one thing. Now let's take this. If I want to calculate this, I simply take this. Let me paste this here. Does the charges change? No, both the charges are the same. So this is the same, this is the same as what we have, this is the same. What changes is this part. So m1 m2 both equal to 1.6 into 10 to the power minus 27. Now if you solve for this, you get 1.3 into 10 to the power 36. So yet again we prove that the force due to the electric charges is much greater than the force due to gravity. Now what can we say by this? We can say that the electrical forces, what about the electric forces? The electrical forces are enormously stronger than the gravitational forces. This is the key takeaway for us. By the way, if you are watching this on YouTube, I would provide the link to this notes which I am using in this video in the description. If you would want to refer the notes for all my videos, they are always there in the description. We have completed the next part. Now let's go to the final part of the question, which is estimate the acceleration of the electron and the proton due to the electrical force. We have the proton here. This is the proton, the other one is the electron. Because they are oppositely charged, they are going to be pulled towards one another. So when they get pulled towards one another, that means there is a physical movement. They are coming towards one another. So when they are moving, they are not going to move in a constant velocity, right? There bound to be some acceleration. Now how do we find acceleration? Acceleration is not a unfamiliar idea. So acceleration is given by force is mass times acceleration. From this we get acceleration is force by mass. But we already know what force is. We are working with the force due to the electrical charges. So I'll go with 1 by 4 pi epsilon naught into, we are speaking about the charges. So the charges Q1, Q2 is the same in both the cases. It's right, Q1, Q2 by the distance between them. So this, I will take it as 9 into 10 to the power 9. We already know that. Q1, Q2 is the same charge on the electron and the proton, 10 power minus 19 square. Then the distance, which is 10 to the power minus 10 meter squared. Am I missing out something? Yes, which is the mass, the question. mass of the proton or mass of the electron. Now this is decided by the frame of reference. Am I considering the acceleration of electron or the acceleration of the proton? Let me to start with consider the acceleration of the electron. The acceleration of the electron, if I consider this, then the mass becomes 9.11 into 10 to the power minus 31, which comes to 2.5 into 10 to the power 22 meter per second square. The same way, acceleration due to proton, so you have to substitute the mass of proton in this. So if you do that, you get the value for acceleration. If you do that, you get the value for acceleration, which is 1.4 into 10 to the power 19 meter per second square. Let us try another question in CBSE textbook again. I will help you visualize this. There is a metallic spherical ball, a metallic sphere which is hanging. Let's call it A. So this is hanging here, but this is a charged sphere. So let's assume it has a charge of Q. Now I have another sphere which is also charged, and let's say this charge is Q dash, and I'm bringing them together and I'm keeping them at a distance of 10 centimeter. Now if we have to assume that both these charges have the same polarity, what happens? They will repel. Now let's look at the force which is acting, the electric force which is acting between them as a result of these two charges. So we could write this as F equals 1 by 4 pi epsilon naught Q1 Q2 R square. So yes, I mean in this case I have taken Q1 as Q and Q2 as Q dash R square. Now what I'm doing is I am making another step, in adding another step in this experiment. I'm taking the same setup, retaining the same setup. So let's look at this. The same setup is retained. Let me remove the distance and all this so that the visualization becomes easier. Yes. Now I bring an identical two spheres near this and I'm touching them. So both the spheres are touched by uncharged spheres. What happened? So this already had some charge in this, so they both carried some charge. The moment it touches, there is a redistribution of the charges. Now this redistribution of charges, mind you, happens only in conductors. If the spheres which I am touching, they are not conductors, rather they are insulators, there will be no distribution of charges. Now there is a redistribution of charges that has happened. This is the second step in our experiment. Now what I am doing is I am taking another step in the same experiment. After they are touched, I'm removing them. I'm removing this brown spheres. So when they gone, they were taken away some charges with them. So what is left would be some charge which is lesser than which previously existed. Now I'm making another important thing here. I'm moving this closer to the point that I have halved the distance. Earlier it was 10 centimeter, now it is 5 centimeter distance. question is, what happens to the force? So you can easily guess it, but if you are not able to guess it, can we try mathematically arriving at it? Let's do that. Force, the formula for force is never going to change. So force is 1 by 4 pi epsilon naught into q1 q2 by r square. Now 1 by 4 pi epsilon naught is not going to change ever, but q1 and q2, there have been some changes in that. Earlier it was q and q dash. What happened is q by 2 went there. So half the force was taken away by the brown spheres, the uncharged spheres. So what is left here would be half of what we initially had. So that way this will be q by 2 into q dash by 2, but the distance, instead of r square, now it is r by 2 square. If you go ahead, q into q dash by 4 into 4 by r square. This is nothing but the same thing which we started with. So what do we learn from this? If the charge, we have two charges, if both the charges are halved, then we can compensate for the electric force by bringing the distance also to half, which is what has happened. We removed half the charge and we removed half the distance. As a result of that, the net force still remains the same. The force remains unaltered.